Good morning, my name is Aljabar from Udayana. I'm from Mechanical Engineering with number 22055311136. The contents of this video is 2.1 Properties of vector, 2.2 Further properties of vector, linear independence, and basis and spinning set. 2.1 Properties of vectors. What are the two attributes of a vector? Length and direction. For example, navigating the earth is impossible without knowing both length and direction of a vector, like Fig 2.2. This one. A vector is represented by components of, for example, east, west, the y-axis, north or south with y-axis, up and down with z-axis. 2.1.1 Vector addition and scalar multiplication properties. Remember, R square forms a plane and R cube is three-dimensional space. Next, we define the two fundamental operations of linear algebra: vector addition and scalar multiplication. Let U and let V and W be vectors R square and K C real number. We have the following result. This dot inner product revisit. This one be vector R. Then the dot product of U and V, denoted by U times V, was defined in section 1.3.6 of the last chapter as U times V equal to U1 V1 plus U2 V2 plus U3 V3 plus and UN Vn. This is the same matrix multiplication of transpose by U by the column vector W. Properties of dot inner product. This one. Next, the norm of length of a vector. Let U be a vector R and the length of norm vector is denoted by U. We can use Pythagoras theorem to find a way to define the norm of a vector. Consider a vector U in R cube, R square. Properties of the norm of a vector. For a scalar K, define the modulus of K, denoted K as this one. Proposition 2.10. Let U be a vector of Rn and K be a real scalar. We have this following. 2.2 Further properties of vector. Revision of norm and dot product. We first do a numerical example of norms, length, and dot product example like this. This is the example. Angle between two vectors. This figure 2.11 shows a constant force F applied to an object, and as a result, the object moves a distance d. The work done by the force is the product of the magnitude of the force in the line of action, F cos theta, and the distance an object has moved, d. Work done equal to F cos theta times d. How can we find the angle theta between two vectors in the above diagram? 2. Inequalities. We prove some inequalities in relation to the dot product and norm of a vector called Squarch inequality 2.14. Let U and V be vector in R and then. Unit vector. A vector of length 1 is called a unit vector. For any non-zero vector U in Rn, we have this one. What does this mean? It means that we can always find a unit vector in the direction of any non-zero vector u by dividing the given vector by its length u. For example, a vector is a particular direction of length 5 can be divided by 5 to give a vector in the same direction, but length 1 unit vector. The process of finding a unit vector in the direction of the given vector u is called normalizing. The unit vector in the direction of the vector u is normally denoted by u accent, pronounced u hat, meaning it is a vector of length 1. That's it. Application of vector. An application of a vector is a support vector machine, which is a computer algorithm. The algorithm produces the best hyperplane, which separates data group. Hyperplanes are general planes in Rn. In support vector machine, we are interested in finding the shortest distance between this hyperplane and the vector. A hyperplane is a general plane in a space, into space in a line, as shown as Fig 2.24. Linear independence. 2. Standard unit vector in Rn. What does the term standard unit vector mean? Unit vector are length 1 and standard unit vector Rn are column vector, with 1 in the position of the vector ak and zeros everywhere else. Why are the standard unit vector important? Because we can write any vector in UR in terms of scalars and standard unit vector. Linear independence. This is the example. We say that the standard unit vector A1, A2, and AN are linearly independent when any one of the vectors AK cannot made by linear combination of the other. One of the reasons we can write any vector Rn in terms of A1, A2, and AN is because these vectors are linearly independent. Linear dependence. What does linear dependence mean? Definition 2.20. Conversely, we have the vector v1, v2, v3, and vn, and Rn are linearly dependent. The scalars k1, k2, k3, and kn are not all 0 and satisfy k1, v1, k2, v2, k3, v3 plus kn, vn equal to 0. This is the example. Properties of linear dependence. In this subsection, we describe easier way to testing for dependence for this example. Basis and spanning test. From the last section, we know that we can write any vector Rn in terms of standard unit vector A and An. We say that the vector E1, A2, A3 span or generate R cube because the linear combination is AA1, BE2, CA3. Produce any vectors in R3, R cube. We define them in span as follows. Definition 2.25. Consider the n vectors is the set of S, v1, v2, v3, vn in any space Rn if a vector can be product by a linear combination of this vector, then we say that this vector generates n space. Next. Basis. We want a simple way to write down our vector. How can we do this? Give some vectors we can generate others by a linear combination. We need just enough vector to build all other vectors from them through the linear combination. This set of just enough vectors is called a basis. Property of basis. Proposition 2.27. Any n linearly independent vectors is Rn from a basis for Rn. Note that this is an important result because it means that given n vector in the n space, it is enough to show that they are linearly independent. To form a basis, we don't need to show that they span Rn as well. For example, we only need 3 linearly independent vectors in R cubes to form a basis for R cube. Number 2, 103 linearly independent vector in R103 to form a basis for R103. Next, we prove a lemma. A lemma is a proposition of theorem, the proof of which is used as stepping stone towards proving something of greater interest. Lemma be a set of m vectors that are linearly independent in Rn then m less than equal to n. This is for today. Thank you.